Great. Okay, my name's Jason Goldschmidt. I'm from Dell Technologies. I work in the office of the storage CTO, and I'm part of a group that's looking at accelerating object storage for AI/ML workloads. And one particular area of technology we want to talk about today is S3 RDMA, or sometimes it's referred to as S3 over RDMA or S3O RDMA. But this is nascent technology that I'm sure a lot of folks here have heard the buzz about. So today I'm going to talk about, well, why? What's driving this? Why are we looking at changing something tried and true like S3 object storage? What goals do we have? What are we trying to solve for? And through what mechanisms? And look at a case study of what we at Dell experienced putting S3 RDMA into our object scale storage server. Okay? So first, let's consider this idea that customers want faster object storage to support AI workloads. We talked this morning, Curtis talked to us about the wide world of AI workloads and how they are different. Okay, so previously, S3 has not been able to be used as a primary data source due to latency. Right? And this performance has prevented adoption of S3 object-based storage for generative AI/ML workloads on-prem. Cloud's a little bit different story. We know that there's a lot of benefits to object. Data scientists seem to love object. Storage administrators. It's simple. It's easy. It doesn't have the same control mechanisms that we would have with file. From a protocol standpoint, it is built for high throughput and parallelization. Right? So trends show a slow but steady increase in object storage adoption for primary storage for AI. Right? But to meet this demand, a faster object storage is needed. Right? This is one that is high performance, delivers low latency, but very particularly is developed for S3, for the S3 API. This is not like a replacement object storage. Those S3 semantics need to remain in place because of the popularity and ubiquity of the S3 API. But what customers want is that significant and measurable difference in throughput and latency for these specific workloads, and maybe for a wider range as we learn more about it. And the intent here is utilizing RDMA because of all the properties that it has as an offload technology to deliver high throughput and ultra low latency for direct data placement. So today we'll talk about how S3 RDMA rise to this opportunity to meet for performance-sensitive applications in the AI/ML space. The goal here, I'll state it, is to achieve file-like performance for objects within a data center environment. That's what we're building for. This will involve using RDMA to perform data transfers within S3. So traditionally, we know S3, the data moves within the HTTP payload of the S3 request. Right? Put object, it's there in the payload. When you send the request, get object, it's there in the response when you receive that at the client. Right? But with S3 RDMA, or to meet this requirement, the objects are transferred memory to memory between an S3 server and client, because RDMA enables that. Right? Additionally, we can utilize technology like RDMA over converged Ethernet so that existing infrastructure can be used. Right? See it through trends here, right? I want something that's faster. I want something that's lower latency, but I don't want to change a lot of things. So to meet these goals, Dell's been collaborating with our partners at NVIDIA to integrate S3 RDMA into Dell object scale solutions. Something we announced back in May and are looking to make it available within the product for customer preview this fall. So this brings us to use cases for S3 RDMA. We consider traditional S3, where data is transferred within that HTTP payload. It's actually very good for producing high throughput data transfer. This is because the S3 API enables a lot of parallelization. We see this in performing multiple range gets in parallel or multi-part upload. Very high throughput. But in order to meet that high throughput, a large number of threads and clients are required to move all that data. So if you have a lot of resources, you can fill the pipe. But AIML workloads are a little different, or at least that's what we've observed, is that they require high throughput, require low latency, but it's performed with far fewer threads on very dense systems. These are AI servers. Right? These are systems that are packed full of GPUs. They have lots of memory, lots of networking fabric, right? And these single discrete systems are super data hungry. And you have very few threads that are driving these data transfers. This morning in Curtis's talk, he talked about the different workloads that are included within AIML. And they split into the categories of our AI training and inferencing. Right? So for our training, we have data loading, indexing, checkpointing. And for inferencing, inferencing presents this very ripe world for looking at data storage needs. One particular hot area, because I've heard it in every single talk I've been in today, and there's actually a talk going on right now. My colleague, Orkanar, is talking next door about it. You should watch it on video later, is KV cache, right? Just like KV cache, I can hear it through the wall. All these things together have these unique properties, and the intent here is to say, well, I believe S3 RDMA can meet these requirements in ways that traditional S3 data transfer could not. Okay. So we'll consider a case study. So Dell Object Scale version 4.1 will be including a feature of S3 over RDMA. And this is based on a model that Dell developed with NVIDIA and their partners. And the way this model works is one where the S3 API requests become more of a signaling mechanism to the server. So we think about how a put object works today. An HTTP request is created. The object data is put into the HTTP payload, and it's pushed over that TCP connection to the object server. In the case of S3 RDMA, that payload is empty. There's no data transferred within that HTTP request. Instead, there is some metadata which indicates to the server how to perform the data transfer and to where, right? So that the data that resides in client memory, and that might be main memory, that might be a GPU, it might be some other device, that data needs to be read using an RDMA read and then persisted as an object at the object storage. Gets, on the other hand, traditionally we would see a response to a get object containing the object data within the HTTP payload. In this case, when that S3 response comes back to the get object, the data already resides within specified client memory location. So these things together, using this model, we saw a net result where there was a reduction in AIML training and inferencing time. Right? That's how we measured it. But there are a few reasons why this is happening. Right? Major one is that the GPUs remain dedicated to what they do best, right? Which is the AIML processing. Right? They're not having to spend GPU resources or utilization on data transfer. Right? The data resides within the memory. It is read from there, or it is written to a specific memory location, which can then be transformed into something like a tensor that might be useful to the GPU. As a result of using RDMA, we see a lower CPU utilization at the host, which means that host CPU becomes available for other things, right? We talked about preprocessing, right? Or whatever it might be, right? Or systems that simply have more discrete CPU available. As a result, we see the maintaining of fast transfer speeds even when the host CPU is loaded. And as a result, we're able to measure this decrease in latency, we're able to maintain this high throughput, and we're able to keep the GPUs running and focused on the job that they need to do. We don't have GPUs waiting for memory copies or for CPU resources to become available to perform data transfers. Okay. Good, it's working. Okay. Now, I heard a few times this morning already, folks talked about data that will ultimately reside within GPU memory, or data that resides in GPU memory, right? If that is the goal, right, which is why we're here, why we're talking about this, for traditional S3, it requires a data copy. Right? Even with the most optimized client and server to perform those HTTP-based data transfers, we still have to copy data from the CPU to GPU. We know that has a cost of incurring that extra data copy. That's been well reported, well measured. But it additionally, for some workloads, will require a large amount of GPU utilization. Again, taking the GPU away from the work that it needs to do. Right? But in the case of S3 RDMA, the memory location utilized could be host CPU, could be a GPU. And with GPU direct technology, that data can be written to or from that GPU memory without the requirements of a bounce buffer within the CPU, without any data copies, and without increasing GPU resources, or I'm sorry, without increasing GPU utilization. And this is where we see the benefit, right? If we kind of thinking about all of these costs today, right? We have this system that can scale to very high throughput, but what we really want it to do is operate on data within GPUs. What is the least resource-intensive way to do that? Okay. So I want to talk about some workloads that we ran to help us understand where the benefits were of S3 RDMA versus inline data requests. And so we looked at a single GPU client system. And it was performing large object gets from a Dell object scale object storage system. And we compared what we refer to as inline. So inline is traditional S3 data transfer because the data is transferred in line with the HTTP request, versus RDMA, which is out of band. And in the first scenario, we just took a completely idled system and say, all right, I want to transfer data using traditional inline from host memory, or I want to perform a get operation into host memory using traditional S3, or I want to use RDMA to do the same. And they perform very, very similar. Right? Again, because if you give an S3 client enough resources, it can perform very high throughput data transfers. And in this case, it meant a CPU utilization that was 20 to 30 times higher than when using RDMA. Using many, many cores within that host system in order to hit a bottleneck versus a fraction of a core. Because now the host CPU is only performing that signaling operation within the S3 API. It's not involved in the data transfer. Since we're using large objects, it means more of the time is dedicated to that data transfer as opposed to the signaling. So great. Traditional S3 performs very well. Why do we need to change it? When we start taking away available resources, we think about that host system becoming very busy. Well, what happens? Well, now there's contention. We can't use all of those cores in order to fill the pipe with traditional S3. So we see a degradation in performance, and that's represented by the second yellow bar. But for RDMA, even though we've taken away these available CPU utilization, it hasn't mattered, right? Because RDMA doesn't depend on that. RDMA is an offload technology. Right? It has the scant amount of CPU that it requires in order to perform the requested operation. And so we see the throughput continuing to hit our bottleneck within our system. Now we think back to our previous slide where data ultimately wants to live within the GPU. Right? So if we think about, we have data that's on our object storage, and we want to load it into the GPU, transform it into a tensor, right? It's the ultimate goal. As we discussed, for traditional S3, that's going to require data copy. Right? For S3 RDMA, right, we can perform this direct operation to the GPU memory. So now we have this system where we've introduced data copy, we're utilizing a lot of host resources, right? And as a result, we see a further degradation in performance for traditional S3, and S3 RDMA remains flat and performant and hitting our system's bottleneck. And finally, in our worst case scenario for traditional S3, it's a busy CPU, we have to copy the memory into GPU. All these things together results in our performance being cut in half, right? Significantly slowing down the system, significantly increasing the time it takes to perform our AIML operation, right? But with S3 RDMA, we're continuing to hit that bottleneck within the system. So, we see this trend, throughput remaining flat for S3 RDMA, but it's decreasing quite a bit for traditional. So to summarize these results, inline and S3 RDMA can perform very similarly if there are enough resources available. but the resource requirement for performing the same data transfer with traditional S3 is 20 to 30 times higher CPU utilization, right? Lots of cores. Cores that might need to do other things. With S3 RDMA, we can utilize a zero copy mechanism to client memory. Client memory that's within the GPU, within the CPU, within another device. Right? And by doing that, it means that we save on a data copy that would normally be there if we had to move between host CPU and GPU. Those data copies we've measured as required up to 40% additional GPU utilization just for data movement. The trend shows that S3 RDMA maintains throughput on this busy system without additional data copies, and yet the performance degrades by half when we introduce all these things with traditional S3. Okay? Because we're doing it all from one system, small amount of resources, and we have specific goals of what we're trying to do. Okay? So we believe that S3 RDMA is uniquely positioned to meet the requirements for AI/ML workloads, right? For these data-hungry AI servers, without the need for spending additional resources just related to data transfer. So this our presentation. I wanted to leave a good amount of time for questions. So let me open up. Hi. Oh, thank you. The question was, what are some of the challenges you faced with doing S3 RDMA? Are you asking about challenges as far as being an implementer or data infrastructure? What might it be? Implementer, okay. Right. So as an implementer, there was certainly a lot of considerations to be given. Right? I think there are tuning that one might consider, right, as it relates to what are the right object sizes where S3 RDMA can provide a benefit, and where might it just be better to perform an inline operation, right? So I think that was one point. Get to very, very small objects. Maybe you just put it into the payload and be done with it, right? Another place was what operations, what S3 operations to add S3 RDMA to. So put object and get object were the two obvious ones. The multi-part upload for to put a part of that upload, that's a different area. And so we considered that and tried to say, well, from a completist standpoint, we may want to add data transfer here, but is there a benefit? Right? We think about why multi-part upload was created to begin with. It's so that you can have more threads performing data transfer at once. But in the case of S3 RDMA, a single operation, a single signal can trigger a large amount of data transfer, which happens like, you know, at the whim of the server implementer at this point. So now the client is far simplified. I want to get an object, I use one API call, transfer the object, it's done, right? So that was another area to consider, is what operations were interesting. When we got down into the implementation standpoint of how the requests and response should change, right, we were working now with the SDKs. So we think about AWS SDK, or particularly the AWS CRT S3 SDK. There's a lot of optimizations that are built into that SDK that will help accelerate data transfer through this parallelization. So it makes the interface easy for developers, and underneath it does some of the splitting of parts, does range gets, it does multi-part uploads, does all this based on configurable thresholds. And so we wanted to have to think about, well, we got to control that, or we have to be mindful of that because maybe there is more value in fewer signals with S3 RDMA as opposed to a lot of small requests. Okay. And one last area I think is an interesting question. There's a lot of data integrity that's built within S3. So performing checksums, performing payload checksums. What are we checksumming here? The payload is empty, right? There needs to be some understanding about what those refer to. What do these signatures refer to? Is the data that is going to be placed, right? Or is it only what is in the payload? So certainly some open questions for implementers. The guy behind Tam.
Yeah, thanks for the talk. Interesting. You mentioned S3 RDMA is uniquely positioned for AI/ML workloads. Yes, but don't you think that RDMA itself will be bound by the scale because the transport protocol inside the RDMA is, if we foresee that would be have a performance bottleneck if the cluster size increases.
Yeah.
Why I'm mentioning is because Dell technology is involved in this UEC consortium, where they're actually working on the transport protocol of the RDMA.
Mm-hmm.
So we'd like to have, RDMA is maybe foresee it's really bound by cluster size, right?
Yes, that's right. You know, if we think about, let me repeat the question. So the question was about, do we see limitations in RDMA itself for cluster scale, as opposed to considering some of the ultra Ethernet investigative work that's being done by folks within Dell and folks within this committee, right? So sure, I think we will ultimately hit fabric limits. We will hit connection and queue-pair limits that may be addressed by other protocols. I think this is very much about these on-prem environments that are being scaled around small number of very dense systems, right? I think if we are considering about the long term, maybe it needs to be less technology focused as far as RDMA, but as maybe something that's pluggable within there. Sure.
Very good. But in this case, for the RDMA, you say it's very good for the large objects. You have what's the size of an object you think is large? And how about, I heard people say, typically most of traffic is a smaller object. So how do you balance, like, the three being only for large objects or for programs?
Yep. Yeah, so I think I will summarize the question. The question was about, for DMA operations, there is a lot of setup that goes involved, right? So this is going to be the connection setup for establishing the queue pairs between the initiator and target, right? And then, what is that cutoff point? What is that where the object size is large enough in order to benefit all of that setup, and where would it be small enough where it might cause an increase in latency, right? And I don't think we've really come to where that cutoff is. I was speaking with my friend Kieran earlier from NVIDIA. Some of his experience has been around the 1 megabyte point, so 1 megabyte objects and above. I think it may be very endpoint specific. With Dell Object Scale, we were seeing some overall benefits going down to 64K. Yeah. Tom.
So we learned what you described in storage over 20 years ago. It doesn't surprise me a bit that there's a huge win here, especially with GPU Direct going peer-to-peer straight to the GPU memory. That's really cool. But what I noticed was you didn't really talk about the protocol, the S3 extensions. Is this a Dell proprietary extension? What's the protocol look like, and where are you going with it to open this up?
Mm-hmm. Okay, so Tom's question was about the protocol itself. And he said that a lot of the things that are presented here we knew 20 years ago, like when Tom and I worked together on NFS over RDMA at NetApp. I wanted to talk about the model for transfer itself instead of getting into protocol specifics. I think there is a importance here of having a representative client-side implementation as well as the endpoints utilizing this. I would not see this as Dell proprietary. We've been working in partnership with NVIDIA. I know they've been working in partnership with other endpoints. So I think there is opportunity for interoperability.
And it tucks into the SDK in a familiar way.
This was the great part. I really thought at first, Tom's question was the changes that are required in order to build an S3 RDMA client, how much does that involve modifying an SDK? Right? At first, I was worried about this. I didn't want to become an AWS SDK maintainer or something like that, or have to feed changes back through Amazon. The SDKs provide a lot of great interfaces that enable the control of adding metadata to requests or reading metadata from requests. And from a get object, put object standpoint, that's really all that was required in order to pass data back and forth.
So you put it in the metadata, but you don't put it on the wire. You do RDMA stuff on the side.
That's right. It's a
Clever.
Yep. It is clever.
So do you require a custom client, and then is the custom client working with some NVIDIA library?
The question is, does it require a custom client, and does it require working with an NVIDIA library? Yes. So I believe a custom client or a custom set of libraries would certainly be required here, right? I was not able to download a S3 RDMA client. Anything we did within Dell, the client, the S3 client, the integration within the CRT we did within our labs. So there is a piece here, and if there are application developers here, to be thinking about what this looks like. And certainly it involved NVIDIA libraries where we were dealing with CUDA memory, right, and utilizing that for the RDMA transfer.
So yeah, my question is like, have you tested under like a heavy condition network, because we're mixing TCP with RDMA, and they have different characteristics under low condition.
So the question was, did we test under network conditions, network load conditions, right? Because TCP has different characteristics than, say, the RDMA and the UDP-based control messaging. We did not. That sounds like a particularly interesting area of investigation. Thank you. My friend back there is very patient. All right, so the question is, when you get object, you don't know the size of the object. Obviously, if you request a range of bytes, right, that's indicating how much you want to read. But if you're just saying get object without any range operation, your get object could return a terabyte object. And so how do you know how much memory as an implementer to reserve, both, let's say, allocate within the GPU and then reserve with RDMA, before you perform the get object, right? And I'm going to hedge a little bit here, right? I think that's kind of implementation specific thing. I've understood that the way a number of these AI frameworks work is that they are allocating very similar size buffers, right? And they're requesting objects that are of similar size. So a lot of that we found was built into the framework itself. I think, head object helps there. It really requires a coordination to know what is being loaded and where, and requesting only a specific amount or less.
But then you would need to run some kind of iteration, so you will not be able to allocate 1 terabyte buffer on the client side, so you will run an iteration of something smaller.
That's right. That's right. So and as of right now, I don't know of any terabyte GPUs that exist. So you are going to be filling multiple memory buffers anyway. If you have multiple GPUs on your system, or you're loading a portion of the model in, or something like that, whatever it may be. Yeah. Tom.
Power. We must save power. How much?
That's a great question. So Tom's asking, this must save power. How much power is it saving? Don't know. This is a question that I've had as it relates to KV caching. I think anytime we're saving gigaflops of compute or GPU compute, there's got to be a power saving. And
all those idle cores.
Yeah. So maybe this is. I would love to see us talk about. I'd love to see us talk about things in terms of power savings. I know it's extremely important to customers. Yep. So the question is, did we change the layout, the data layout on the object storage, on the object server, as it relates to, say, erasure coding or redundancy? We did not. We built this within the data movement mechanisms that we already have today within ObjectScale. We have a scale-out cluster that supports erasure coding. And so a get object is going to read in that data from multiple sources and then perform the RDMA data transfer.
What's the object size that when you tested it for a single GPU test? What was the object size for that?
That was a 5 megabyte object. Yeah.
So coming back to the protocol, so we talk about there's a custom client, and so switches means we are not running the standard S3. Otherwise, we could have just used AWS SDK. So it's still active looking for to form some along with the community to form some common standard for S3 RDMA protocol. Because there are multiple vendors already announced that we are working on S3 RDMA. So if that's something they will be interested.
Right. So the question is there any efforts to standardize the protocol? Right. Well, I think the intent here is we all want interoperable systems, right? We all want to not have to rewrite our clients based on which endpoint we're using it. And I think a lot of the implementers and vendors here have the same goals. Yeah.
How is the RDMA connection managed? Is it created per request, like I'm getting a request, oh, it's an RDMA request, let me open a connection, or is it a pre-existing connection or a long-lasting one?
Yeah. So the question was about connection management for RDMA from the initiator to the target. We've looked at this a number of different ways. There's a number of different RDMA connection styles, be it reliable connections, which tend to be static, or dynamically connected queue pairs. right? And depending on which connection model you use, you might be managing those differently. So in our work, we built a number of prototypes, and we did look at the different connection models. So something like dynamically connected queue pairs is interesting because it means that you're setting up that queue pair on a per request basis, right? Maybe some optimizations within the initiator. But for RC, that's where you have this point-to-point setup, and you may have those setups run for a longer period of time. You may do some connection caching. We saw some benefits with that. Yeah, so I think it may depend on the connection style. Yes?
Have you developed any specific test suite?
Oh, okay, yeah. Yep, have we developed any particular test suite? So say, good time to plug the BOF that we're having later today. So one of the things we'd like to discuss is what are those test suites that folks are using for testing fast object, high performance object, even S3 over RDMA. We hope to give a quick demonstration of a tool we are developing at Dell. I have Mike Horgan here, my colleague. He's going to run that demo and hope to get some interest, feedback, good conversation going about fast object and S3 over RDMA. The BOF is at 8 o'clock tonight, and it's in this room. I have 10 minutes left. Yes?
What kind of data do you use? Like, is it for training or retraining models?
Yeah. So the question is, what kind of data do we use? Was it data for pre-trained models? What was it, right? Yes and no. So yes, we did work with data that related to pre-trained models, especially when we were looking at data loading and checkpointing, right? In other cases, we were dealing with synthetic data because we were trying to really establish what the speeds and feeds were of the system. Yeah.
Were there any unique security concerns given RDMA is quite a different security landscape than TCP?
The question is, have we considered any security considerations as it relates to RDMA because the security landscape for RDMA is very different than that for TCP. This has come up. I'm not the best person to talk about it, so I am sorry.
Well, the data integrity check, what kind of, we know AWS has MD5.
Mm-hmm.
So do you calculate MD5 or do you support checksums or the other? Because that also affects performance, right? What's your view about that?
Great. So the question was about data integrity, which checksum algorithms that we use. AWS uses MD5. I think that they've moved to SHA, NVMe. Yeah. Right. Right. So this is a very good question. I think this is currently a open area of discussion about what you are performing the data integrity against. Right? Is it the memory location or is it the request response itself? Right? And we were not certain about the answer. So we were not sure what client implementers would build. So I think this is certainly an area for discussion where folks who are building clients, I want to learn what this is and learn the best way to continue to provide data integrity checks with RDMA transferred memory locations.
There's also the question of who provides the integrity. Since you're transferring it directly to the GPU,
Yeah.
it may not be a traditional model.
Yeah. So Tom's point was that it's who is providing the integrity If you're transferring the data to the GPU, right, that may not be clear. And I think part of it is how to do this in a optimized way so that you can continue your operations and not pull the data out of the GPU. So it's definitely a good area of investigation. Kieran, I'm sure you have great ideas about how to do this. No? Maybe? Okay. Yes?
I think the last couple of questions, there was like a lot of properties from the original public cloud object stores. That one of them was availability zone. Which obviously also is given up here to get performance. Do you think that's permanent? Do you think there will be forever another copy of the data in a not availability zone system? Or do you think that with Rocky over time, technology will evolve and there's a way to get enough safety also against data center failure in this setup?
Okay, so the question is, does this forego availability zones as we think about that for object technology? I have not considered that question. I think I do not believe it would change anything, right, as far as having multiple replication of data across different data centers. But thank you for bringing that up. I think that's something to noodle on a little bit. Yeah. Anyone? All right. It seems like that's it. Thank you very much. Appreciate it.